going to give you the very simplest version of it, which is, of course, all a theorist can really manage. And so Henric's research vision through his career has been to find out how black holes and neutron stars shine. And to do this, he works on detectors and telescopes that allow us to see jets of radiation that they spew out by looking across the electromagnetic spectrum, X-ray, gamma ray, and radio, and seeing how these large black holes are the most powerful accelerators in the universe. And even the smaller black holes are very interesting, whereby small, this is astrophysics, so small means the size of our sun, or the mass of our sun, not the size of our sun. And looking at how the X-rays come out of them. And this data is very interesting. It's got potential for fundamental discoveries like testing general relativity, Einstein's theory of general relativity. Are black holes the very bare things that Einstein tells us they are with very few properties? You can test that by looking at the X-rays that come out of them. Testing our theories of electromagnetism, the extraordinary electromagnetic fields that exist around these objects gives you an opportunity to see if we think we understand electromagnetism very well, but you don't know until you test it in the extreme case. And testing models that go beyond our current theories, models that predict unexpected surges of X-rays or gamma rays from things like dark matter annihilating. You may find those by the sort of detectors that Henric works on. He does, I should say, both things that need to be done here: the development of numerical codes, computer programs to simulate these high energy sources, to model them. And also he's a leading developer of X-ray and gamma ray detectors and of missions to use those detectors, particularly the polarization of X-rays. And I should say that this is very difficult. An X-ray is not an easy thing, right? You're probably all slightly scared of them. And it's like sort of little bullets being fired at you. And X-rays, they're absorbed by the atmosphere, so you can't just set out your detector on the back lawn. It has to go up above the atmosphere in some way or other, often through balloons, like as I'll say in a minute, or up in orbit. And what Henric is measuring is the polarization of X-rays, which is kind of like, if I fire a bullet at you, can you measure how it's spinning, right? It's not easy. It just wants to go straight through. So he's one of the leading figures in the development of these detectors. He's on the science team of NASA's IXPE mission, Imaging X-ray Polarimeter Explorer, and he's now the principal investigator of XL Caliber, a polarimetry mission, which means measuring this very difficult polarization, which uses balloons to get above the atmosphere, and has already had one mission. They send them from Sweden, a good excuse to go up to the north of Sweden, and they're going to do another one this year. And so you'll hear more about Henric's science. Let me also just say that Henric is a great contributor to the department and the university. As you just heard, he's a founding member of the Center for Quantum Leaps, which is one of the signature initiatives of our strategic plan. He's played all sorts of important roles in the department. I don't want to name them all, but he's been a very reliable and wonderful contributor to the life of the department. He's also a dedicated and innovative teacher. He kicked off our very first freshman seminar, which we'd never had one before, shockingly, and taught that, and that's been a success, and he's going to carry on doing it, we all hope. And on top of all this, he's now chair of the department. So he is now in the position of leading the department through this unprecedented bout of hiring that we've just enjoyed, getting new faculty, and he's going to be the one guiding these new faculty to achieve what we hope will be a transformative impact on the department, the School of Arts and Sciences, and the university. So it's an enormous pleasure to be here to introduce Henric.
Henric, I present you with this medallion as a symbol of your new appointment. And the front reads, Wilfred R. and Andy Konneker, Distinguished Professor in Physics, Washington University St. Louis Arts and Sciences. And engraved on the back, Henric Krawczynski, February 29, 2024. And here it comes. I'm gonna tell you that Anka hasn't done this right. You're supposed to wear this thing 24/7. 24/7. So only Alina can help you. It gets too heavy. Okay. You need a photo?
Does this work? Okay. Thank you so much for being here. This is really overwhelming. It's a great honor. And so nice to have everybody together here. So I want to talk a little bit about the research. Maybe first thank Feng Sheng Hu for the introduction, for the strong support of the physics department. We just hired 5 people and are really enthusiastic, 4 people, really enthusiastic about it. We'll also very much thank Barbara Konneker-Webster for coming today, flew in from Baltimore. So that's wonderful. I got a book about Wilfred Konneker. I will read this. I'm very interested. And want to thank Mark Alford from whom I took over the department 2 years ago in an excellent state. Want to thank very much the physics department. Always amazed that we can find common ground and agree on important decisions. As you will see, a lot of the work that I do is teamwork. So I'm very grateful for all my graduate students, undergraduate students, technicians, engineers, and fellow faculty members to work with me. It's greatest pleasure, and we spend a lot of time, and it's time very well spent. Not only because of science, but because it's a lot of fun to be with everybody. So show here, that's a picture from a balloon launch 2 years ago in Yukosjärvi, 67 degrees north. We'll go again this year in April. We spent actually probably 6 to 2 months there, and then in August we go for a second ballooning campaign to Fort Sumner, New Mexico. So there's a lot of travel this year. Briefly wanted to say about Wilfred R. and Anneli Konneker, who endowed this chair. They looked at a lot of photos of them. They always looked like very much in love. It's such a characteristic thing that you see them, that they were very happy together. So that's beautiful. They were very generous philanthropists, made very significant donations to Washington University, Ohio University, and to a lot of the St. Louis staples of the institution that we all love, like the Coker Dance Theater, to which a lot of our kids go, or the Hippo Pass, I think, in the St. Louis Zoo. Anne Lee Konneker, she was centrally involved in renovating a few buildings at Ohio University, for example, this Konneker Alumni Center. And Wilfred Konneker was a nuclear physicist, and I looked up some papers from him, and this one actually directly impacts the work I'm doing also. It's about the annihilation of matter and antimatter. You maybe know that if the lightest matter, which is electrons, and antimatter meet, when they meet, they just annihilate into pure energy, into 2 or 3 photons. And if it's 2 photons, they have exactly 511 keV. So it's tell you later, we try to detect that or try to study that emission from the center of the galaxy. But Wilfred Konneker, he studied the angle between these 2 gamma rays, which is actually really important for nuclear medicine. Wilfred Konneker, he established like 7 companies, as Dean Hu said before. And so he was working on nuclear isotopes for diagnostic purposes in medicine. Let me briefly talk about black holes. So black holes, they have masses, the ones we know, between something like 5 and 10 billion solar masses. The smallest one are only like 20 kilometers or 10 kilometers diameter. The largest one is bigger than the solar system. They all have in common that they're really compact given their size, and they're so compact that gravity becomes really intense and not even light can escape. Their modern description of this is based on Albert Einstein's theory of gravity. And in that theory, matter and energy curve spacetime. And then matter tells spacetime to curve, and spacetime tells matter how to move and clocks how to tick. And this is one of the most beautiful theories ever developed. It's useful for GPS, for internet, for space flight, and it describes the history and evolution of the universe. Working with that theory has been one of the biggest joys of my career, because it's just it's a very elegant theory. The modern kind of the foundation of black holes were laid by Krawczynski and WashU. They found the first solutions, or the one and only solutions of Einstein equations, the vacuum solutions that describe black holes. In this, we kind of understand what black holes is. So if you're inside a black hole and shine your laser pointer away from the black hole, the light goes with the speed of light through space, but the space-time goes even faster to the singularity. So it will kind of take you and the light into the singularity. Here, John Wheeler has a nice quote that emphasizes how extreme black holes are. So it says, the black hole teaches us that space can be crumpled like a piece of paper into an infinitesimal dot, that time can be extinguished like a blown-out flame, and that the laws of physics that we regard as sacred, as immutable, are anything but. So it just shows you that at the centers of black holes, kind of all theories actually fail, and we still don't know what's there at centers of black holes. In the last 10 years, there have been amazing new results for black holes. A lot of them, some of them come from experiment, but a lot of them come from supercomputer simulations. We can now simulate black holes merging and compare that to the observational data. Very similarly, there are now very detailed computer simulations of how matter spirals around black hole, similar to water going down the drain. It heats up and then makes a black hole shine very brightly. And this can now be studied from first principles in simulation and compared to observations. As I kind of was already mentioned, black holes have a bright side, and they're mostly bright if they're close to matter and can swallow that matter. So that matter kind of spirals, goes around, heats up to millions of degrees sometimes, and emits X-rays. So I kind of, right now with my research group, we mostly look at the small black holes, or the low mass black holes. They have 20 solar masses, something like 60 to 120 kilometer diameter. And they shine because they're close to stars, and then they suck some of their matter in. The studies are complementary to supermassive black holes, and you probably have seen that in the media. There's this supermassive black hole, the first one which was ever imaged, M87, at the center of a galaxy cluster, the galaxy cluster. So that weighs like 10 billion solar masses. It's bigger than the size of the solar system. And the studies are complementary because they grow in different regimes. This is very low luminosity, and the other one is very high, relatively speaking. So we measure polarization, or that's kind of what I did for the last, we kind of have been working for the last 12 years on. Light transport electromagnetic fields, and usually they go in all directions. But if the light is polarized, there's a preferred direction for the electric or magnetic field to oscillate. And that has actually a lot of information. For example, that's a simulated image where you see kind of the bright emission around the black hole. And the bars show the polarization direction and the degree. Far away from the black hole, the emission has low energies, and it kind of shows the orientation of the accreting disk of matter. If you go to higher energies, the emission comes from very close to the black hole. A lot of photons spin around the black hole, kind of orbit the black hole, reflect, and get highly polarized. And so by measuring the energy-dependent polarization, you can constrain how fast the black hole spins. And basically, this kind of amounts to testing the theory Einstein's theory of gravity in extreme circumstances where gravity is super, super strong. So I just want to show you a single result that we obtained, and Nicole has been instrumental in analyzing the data. So this is an observation with a satellite launched by NASA and the Italian Space Agency. And it's a large team of 110 people, and I was kind of lucky enough to lead this observation. So we look at Cygnus X1. It's a stellar mass black hole, 22 solar masses, some 6,000 light years or so away from us. Has if you had X-ray eyes and would look into the night sky, you would see Cygnus X1 very bright. It's very often the very brightest source in the sky. So we look at it with all kinds of different telescopes. This is from the literature. So this is only shows a region which is only a millionth of a degree. And if you zoom in that much, you see this matter outflow, which we call jet. It's kind of plasma, even though most matter falls into the black hole from the companion star, some plasma bounces back and makes this jet. It's like when you drop a bucket of paint and the paint shoots out. So this is billions of kilometers, and with X-ray polarization, we have for the first time a chance to relate this outflow to what happens very close to the black hole. So the X-ray emission comes from a region that's only like 1,000 kilometers in diameter, and the black hole is only 60 kilometer diameter. And we can basically look in here by 1,000,000 times and see how the matter is oriented relative to this gigantic outflow. So there were kind of two hypotheses of how this would look like. Let's see if this works. Either the gas could be above the black hole and below in kind of a stream of matter, or it could be kind of more horizontally above and below the accretion disk. And these have very different signatures when we look at the X-ray polarization. For example, in this here, it depends on how X-rays scatter. When they scatter, they acquire polarization. So if they scatter up-down, the polarization is perpendicular to this jet. And if they scatter left-right, then the polarization is parallel to this outflow or jet. So now comes the result. Doesn't look very spectacular, but so for the first time we ever measured this polarization, and it's here kind of direction is on top of it. And you see that it's perfectly parallel to the jet, and which seems to show that the gas is kind of parallel to the accretion disk, and then this scenario can be excluded. So this is excluded. There have been like 3,000 papers written about this. Seems to be that this is right. And why do we care? Before I got there, wanted just to mention this kind of interpretation sounds reasonable, but we had to run 60,000 different geometries, simulate 1 trillion of X-rays to kind of make this watertight and have some models that we can compare to the data. So this we did at the Washington University Research Infrastructure Services and used their 5,000 computers for 2 weeks. And to simulate these curved trajectories around the black hole. Why is this important? This hot gas illuminates accretion disk, that X-rays get reflected. The kind of interesting thing is that some of the atoms are iron atoms, and these emit a very narrow, what we call a line. They have a very specific energy. So the interesting thing is, if this gets close to a black hole, the energy of these photons measures how fast clocks move. The higher the energy, the faster clocks move. The lower the energy, the slower the clocks move. So we basically have like clocks everywhere now. And the interpretation of the results depends on how this gets illuminated. Now, knowing now how the hot gas is distributed, we can map out better the space-time around the black hole. So knowing the shape and location of this hot gas which emits the X-rays allows us to map out the black hole space-times more accurately. And because that tests Einstein's theory, and Einstein's theory describes the evolution of the universe, that's kind of a worthwhile thing to do. Just wanted to mention, so we do roughly 50% of our studies is theoretical and computational, and 50% are experimental. So the experimental work is funded very generously by NASA and the NSF sometimes. Overall, like a large number of astrophysicists studies this, like maybe 5,000 or so. We are in friendly competition with national laboratories like the Goddard Space Flight Facility, which has something like 3,000 employees. So the question arises, why are we competitive? And a few answers, of course, we have like a lot of different disciplines together. That's really good because you learn from your colleagues from different disciplines. Because we have a shallower hierarchy, we can do things faster and at a lower cost. But the biggest thing why we're competitive is that we have human capital, namely the graduate students. And every national lab is very jealous of our graduate students. And that's why we can play a role in these big teams, because we have a strong team of graduate students. Briefly wanted to mention how this development works from a concept from a scientific problem to the solution. And that's kind of the thing I learned from Jim Buckley. He told me that when I came to WashU. You usually start with some science question. Sometimes you kind of first find the technology and later the science question. But usually you should start with the science question. You then identify which physical process can be used to measure something better than anybody has measured before. And you identify a detector technology. For example, for our X-ray polarization, we use some very heavy semiconductor detectors. We get some seed funding for this center. The McDonald Center for Space Sciences is absolutely essential for us, because you have to demonstrate you can do it before they give you money. We hope in future the Center for Quantum Leaps will also have some more money to help us to get running. We then mature the technology with our excellent engineers like Richard Bose and Paul Dockham and Isabella Pastrani. And then this puts us in a position to propose missions which are either balloon-borne or space-borne. This entire process takes at least 5 years, sometimes 15 years or 20 years. So it's kind of a lengthy process. So you should make sure you have a good concept once you start that, because then you're stuck with it for a long time. There's some, the technology we develop in dialogue with other fields. So the X-ray detectors that we do are also relevant for medical applications. We go to the same conferences with medical researchers. And so there's another justification for our work that it also benefits medical purposes or other applications. Wanted to briefly, so we have been working for the last 15 years on this balloon-borne experiment. That's kind of that's kind of a pre-stage to launching a satellite. You see this is a picture from Sweden from 2 years ago. This weighs like 3,500 pounds and goes 125,000 feet, so 38 kilometers high. It is then above 99.97% of the atmosphere. And at that altitude, the atmosphere becomes transparent to X-rays, and you couldn't observe them on the ground. Briefly wanted to mention how important it is how important teamwork is in this context. For example, this shows graduate student Lindsay Lizalda. She developed the technology to make a 12-meter optical bench out of carbon fiber and aluminum joints that we do in our shop. So Lindsay pulled a lot of joints for 25,000 pounds until they broke, to show that this can survive even the deployment of the parachute after the telescope did its observations, where you sometimes have 20 times Earth's acceleration. Then we have graduate students Ephraim Gao, Nicole Rodriguez-Cabero, and Andrew West. They all played a crucial role in setting up the software to read out the data and to telemeter to the ground. And I'll come back to this later. Yeah. Richard Bose developed the readout system. And you see here, like the photons come, hit at the stick, it scatters, it gives away the polarization. And then they're read out with some custom-made electronic chips. And we have excellent technicians, Gary Simberger, Dana Brown, Kenny Schmidt, Dennis Hülsmann, and Todd Hart, who play a crucial role in putting this together. Also have senior colleagues, Fabian Kieslag and Brian Rauch. Fabian was a postdoc, is now an assistant, soon to be associate professor at UNH. And Brian has been helping me for a few years on the side, being the senior person when I have to leave. The other people that I haven't highlighted are from the Columbia Scientific Ballooning Facility, Hiroshima, Osaka University, ISS JAXA, and from Stockholm. So it's a big collaboration. So we launched once in 2018 from McMurdo, and we were supposed to fly for 50 days, but after 1.5 days, the balloon lost altitude. So we got some results and observed a neutron star that you see there, and observed its pulsation once every 600 seconds or so, and constrained a bit the polarization, not as well as we would have liked because of the short flight. We had another flight in Corona, so that wasn't so good. So we'll have to repeat this year again and hope this time we get really amazing results. A few pictures. This is from the launch when the payload is elevated. It went up July 12, 2022. And then this is a picture seen from the ascent, and you see that the atmosphere already becomes transparent because you're so high above the atmosphere. And then the balloon flew all the way from Sweden to northern Canada, close to Yellowknife. And then it lands with a parachute to let the helium escape, detach the balloon, land with a parachute, and then we cover the experiment, and nothing was broken, so we can pretty much reuse it. That was recovered by Dana Brown with some colleagues using helicopter. Let me briefly say that the graduate students are not only working in the team, but are full-fledged scientists in their own right. So each of them has written like already beautiful paper. Lindsay about plasma outflows from black holes. Ephraim about new particles, axions being kind of generated close to in neutron stars. Nicole about some special state of one of the black holes. And Andrew about like thick accretion disks. Oh, sorry, this is kind of... want to briefly, before I end, show you a second experiment we have been working on for the last few years. That's actually directly related to the research of Wilfred Konneker. And I mentioned when the lightest particles, electrons, positrons meet, they emit this very characteristic gamma rays. And this is not very common, that emission, so you wouldn't assume you could see it from an astrophysical object. Turns out that previous experiments have mapped this emission, and there's a really strong emission coming from the center of the galaxy. So nobody knows where it comes from. It could be dark matter. It could be maybe exploded supernova remnants, exploded stars, supernova remnants. So we want to build detectors and test the origin of this emission. So what you use is a project together with the Center with a quantum sensing group at NIST at Boulder and University of Colorado in Boulder. And so we use like superconducting absorbers together with superconducting quantum interference devices and some of the fastest electronics in the world, digitizing data at gigahertz. All of this, we started an R&D program where we kind of want to make a more modular system so we can make massive detector systems which have enough effective area to see gamma rays from the center of the galaxy. And this will get energy resolutions for the detectors 20 times better than the best conventional detectors which exist today. So this gives us new possibilities to study the origin because you can measure the line of sight velocity very accurately. And for example, we hope then to detect substructure in this line, and that substructure gives away how fast the matter moves towards us or away from us. So if you combine that with some more spatial information, you can kind of constrain the origin of this emission. So right now we're kind of preparing, you see here, the assembly of the gondola, and Kun and Matt are assembling testing the refrigerator. The measurements have to be done at 75 millikelvin, which is really cold. We hope to launch this in August or September. And then this is only the first experiment. Maybe in 7 years, we will fly a follow-up balloon, which looks at the galactic center and would measure the line shape of this gamma ray line. Then maybe 5 to 7 years later, one could launch a telescope that has angle resolution and can look better at the center. And then maybe another 5 to 7 years later, one could have a satellite mission. So I'm not sure if I'm around at that time. More likely not, but that's kind of our plan. Let me wrap up. So you might think that black hole physicists are lonely creatures that look at very dark objects. It turns out that we look at the brightest objects, some of the brightest objects in the universe. And the best of all is that we are a large, diverse group of physicists, scientists, and technicians who all work together and together can get more accomplished than any one of us could accomplish on their own. And on top of that, we enjoy tremendously working with each other. And this collaborative aspect of the research is the true bright side of black holes. Thank you. Thank you. Okay.
Thank you, Henrik, for a truly fascinating presentation, and congratulations to you again. I actually have been talking to Henrik about making a field trip to some place with him at some point. So I'm looking forward to serving as Henrik's research assistant sometime. I want to thank all of you for joining us to recognize Henrik's accomplishments and to celebrate the generosity of Wilfred and Andy Konneker. This concludes the formal portion of today's ceremony, and please join us for the reception over there and offer your congratulations to Henric and his family.